Hello everyone, this is Dr. Webb. Over the last couple videos we've used vectors to develop some important geometric tools such as the dot product, the cross product. So now we're going to start applying them to solve some problems and look at some other basic things that we've known and love from before. So let's start out talking about lines. Okay, so let's start off with this in R2, but most of what we're going to talk about in R2 is going to apply to R3 as well. So we know that vectors lie on a line, and in fact, the simplest kind of line we can think of is one that goes through the origin. And so if we have some line L like this, well, we can take any vector lying on that line. Let's call that vector v. And then for any other vector lying on that line, that vector, let's call this one w, is going to be a scalar multiple of v, right? And so we've seen that w will be a scalar vector, a scalar multiple of v. And so if we have v, let's say it's AB, then that means that there's some t such that w is going to equal a times t times b times t for some t, right? And actually, as we change this t and we just look at a times t comma b times t, this is actually going to give us all the vectors on this line. So from at comma bt, as we change t, we get all the vectors that lie on the line. And in fact, the components of ATBT correspond to the points on the line. Right? And so this gives us what's called a vector function. We'll call it R of t, at comma bt. So we're using the variable t because it's a non-spatial variable. We're trying to separate ourselves out from x is talking about the x direction, y is talking about the y direction. T really can be talking about anything. And so as we change this t, we get our x and y coordinates on the line. So this is an example of what's called a vector function. We'll be talking about vector functions a whole lot coming ahead. So example of a vector function. Okay. And so this works for lines that go through the origin. But of course there are lots of lines that don't go through the origin. So what can we do for that? Let's see if I can get my big eraser going. There's the big eraser. Okay, so let's clear out space. And now let's try and do the same sort of thing for a line that doesn't go through the origin. Okay, and so this slide is called the point vector form of a line. So let's focus on that. Let's focus on let's suppose that we have a point on the line and then a vector that's parallel to the line. What can we do? Oh, why are you getting smaller? I don't really totally understand this erase tool. It does not do exactly what I would think it should do. That's okay. Okay, that's cleared out enough. Okay, so there's my XY plane. Let's take some point x naught, y naught, take the line going through that point, and then let's take some vector v AB that lies on that line. Okay, and so now we want to think about what the other points on this line are going to look like. Okay, well, if I take some other point up here, let's call it xy, well then I can create a vector that goes from x naught, y naught to xy, and that's going to be on my line. That's going to be parallel to v, because v is on the line, so it's going to have to be a scalar multiple of v. So we see that this vector x, y, that's not what the vector is. Vector, its initial point is x naught, y naught. Its terminal point is xy. So that vector there is going to be x minus x naught, y minus y naught. And that's going to have to be some multiple of AB, same as we saw before. Right? And so, in fact, if we want to solve for the x and y here, what are they going to look like? Well, it'd be xy, I'm subtracting off x naught, y naught. Is equal to t times a comma b. And so then, solving for xy, it's going to be x naught, y naught plus t times ab. Okay. And so, and as we change t, again, same as before, when we change t, we're actually going to be able to get all the points on this line. Let me try and erase this a little bit better. Okay, so as t changes, we get all the points xy on the line. And so that's just going to give us another vector function. So in this case, r of t is going to be x naught, y naught plus t times a comma b, which we can rewrite as x naught plus at comma y naught plus bt. And so these components here, these are going to give all the points on the line. Okay, and so written that nicely up here. In R2, the vector equation of a line through the point x naught, y naught along vector AB gives us right here. So these components here, these are giving us points on the line. These correspond to points on the line. We could go through the exact same construction in 3 dimensions. It doesn't change a thing. And get ourselves a vector equation for a line through, now it's a point in 3 space, so it has 3 coordinates along a vector with 3 components, and we get the exact same idea. So lines in 2 space and 3 space are really pretty straightforward. This should not be b sub t. This should be b times t. Same thing here. B times t. And so that gives us our vector equations for lines. So one thing, so this is a type of, these vector functions, this is a type of what's called a parameterization of the line. Really what a parameterization is we are breaking up the coordinates separately. So if you think traditionally about a line, you have something like y equals mx plus b. So in that you have the 2 coordinates y and x in the same equation together. What a parameterization does is it actually separates them and expresses them separately in terms of some other variable called a parameter. In this case, t is the parameter. And so it's saying this is, it's sort of like, if you've ever, thinking about something moving along a map and breaking up longitude and latitude. This is the exact same idea as that. And we're going to be talking a whole lot more about vector functions and parameterizations over the next couple videos. So I'm going to hold off on going too deep on that right now. So what about planes in R3? Okay, so if we have some plane, it's just some flat space in R3, we can even take some point on it, call it x naught, y naught, z naught. Well, if you think about even given a plane and given some point, there's a whole lot of vectors you can draw from that point, using that point as initial point and going around. In fact, you can do a whole circle of vectors coming out of that point. And so sometimes it's kind of hard to think about a plane in terms of the vectors in it. You'd rather want something that's sort of unique, that's not going to change, right? So what can we put here that isn't going to change? Well, rather than thinking about stuff that's on the plane, if instead we're going to think about things that are perpendicular to the plane. So while there's lots and lots of directions on the plane, there's only one line that's going to be perpendicular to the line. So given any plane, there is one line perpendicular to it through each point. So rather than thinking about directions on the plane, it's going to make a whole lot more sense to think about directions that are perpendicular to the plane, right? And so if I say I'm going to take some vector perpendicular to the plane, since it's perpendicular or orthogonal, another name for that is normal. I'll label it as n. So I'm going to let n be a vector normal to the plane. And so this is just a fancy way of saying perpendicular. Well then, if I have my starting point x dot, y naught, z naught, and I pick some other point on the plane, x, y, z, draw a vector between those 2 points, look at the vector x minus x naught, y minus y naught, z minus z naught. So this is between 2 points on the plane. So this vector lies on the plane. Well, if it's lying on the plane, then it's going to be perpendicular to n. And so if we let n be ABC, so what's our trick to find if 2 vectors are perpendicular to each other? Well, that means if we take the dot product between the two, we're going to end up with 0. Okay, so if we dot x minus x naught, y minus y naught, z minus z naught with ABC, we're going to end up with 0. And so that's give us what's called the point normal vector of the plane. So as we were saying, rather than worry about directions on the plane, we're going to focus in on a vector perpendicular to the plane. So we're going to define a plane using a point on the plane. Point, for these purposes, we're going to call it x, y naught, z naught, and some vector perpendicular to the plane. Since it's a normal vector, we'll often use n for it. Maybe we'll say ABC. And so this is going to give us the point, what's called the point normal equation for the plane. And this is using the fact that x minus x naught, y minus y naught, z minus z naught, as we saw before, this is a vector on the plane. ABC, this is perpendicular to the plane. And so they're perpendicular to each other. And so if they're perpendicular to each other, the dot product is going to be 0. And when we multiply them out, multiply out this dot product, this is the equation we get. And so this is what we're calling the point normal equation for a plane. Okay, so let's do some examples with this actually going through, right? So in this example, we're given that we want a plane that contains the point 2, 1, 3, and we also want it to have the vectors 5, 4, 0 and 8, 1, 8. So these are lying on the plane. Okay, and so if we have 2 vectors lying on the plane, we need to find the normal vector. And so what do we know about n? Well, it's going to be perpendicular to these 2 vectors. So, given 2 vectors, how do you find a vector that's perpendicular to both of them? Well, we went over this recently. We're going to use the cross product. So we can set n to be equal to the cross product of these two. And remember, it's that fancy determinant. It's got a, j, I, j, and k on top. We got 5, 4, 0, 8, 1, 8. And so going through, I times 4 times 8 is going to give me 32i. Let me copy these out. J, 4, 1. J times 0 times 8, that's just going to give me 0. K times 5 times 1 is going to give me 5k. Going the other way, I have 8 times 4 times k. And so it's this minus 8 times 4 times k is going to give me 32k. 1 times 0 times I is going to give me 0i, and then 8 times 5 times j is going to give me 8 times 5 is 40j. So putting these together, I get n is 32i minus 40j, and then plus 5 minus 32 is going to give me minus 27 for k. And so there's my vector n, there's my normal vector, and so then I can do n dotted with x minus 2, y minus 1, y minus 3, and I get the equation of the plane. So 0 is equal to n dotted with x minus 2, y minus 1, z minus 3, and so I get 0 is 32 times x minus 2 minus 40 times y minus 1 minus 27 times z minus 3. And there's my equation for the plane. Okay, next example. So now we're going to find the equation for a plane if we're just given 3 points on the plane. And so that's all that we need to define a plane, is to know 3 points on it that aren't all on the same line. Okay, so in the last example, we figured out how to get the equation for a plane if we had given a point and 2 vectors on the plane. So how can we work that in here? Well, now we've got 3 points. If I just pick one point to sort of be the initial point, so let's pick 4, 3, 1, well, then I can create 2 vectors going from 4, 3, 1 to these other 2 points. That's going to give me 2 vectors on the plane. So let's let v be minus 3, minus 4, 3 minus 4, let's say 4 minus 3. It's important to keep these (4 minus 3), and then 7 minus 1. And so that's going to be minus 7, 1, 6. W is going to be 6 minus 4, 2 minus 3, 3 minus 1. And so that is 2 minus 1, 2. So now these are 2 vectors on the plane, so I can get the normal vector by taking the cross product of these 2. And so that's the determinant of I, j, k, minus 7, 1, 6, 2, minus 1, 2. Copy out those columns. Okay, so this determinant's going to be 2i, 6 times 2 is 12j, minus 7 times minus 1 is 7k, minus, going the other way, 2 times 1k, minus 1 times minus 6 gives me minus 6i, and then 2 times minus 7 gives me minus 14j. And so this tells me n is equal to 2 plus 6 is 8. 12 plus 14 would give me 26. And then 7 minus 2 give me 5. Right. Let's just double check. Dot this with 8. 826 with minus 7, 1, 6. 8 times minus 7 is minus 56. So minus 56 plus 26 plus 30 equals 0. Yeah, so that works. 2 times 8 is 16. 2 times 5 is 10. Minus 26, yes. So this is perpendicular, both of them, so that works. So then putting this together, let's use the 0.431 again. I get that the equation for the plane is 8, 26, 5, dotted with x minus 4, y minus 3, z minus 1, and that's going to be equal to 8 times x minus 4 plus 26 times y minus 3 plus 5 times z minus 1. Okay, and so there's my equation for this plane. Okay, last but not least, so in this equation, we are given a plane, and then we are given some point. So we have a plane. What do we know about this plane? Well, looking at the equation, reading off what's inside with the x, the y, and the z, I can get a point on the plane. And so it's going to contain the point. Reading this off, I have 2, minus 1, 4. And then looking at the 3, there's a 1 there, and a minus 2. That's giving me the normal vector, n. And so this is 3, 1, minus 2. And so then the question is, if I have some other point, this is not in scale in any way, I'm just drawing this. This is not in proper orientation. But we just have some point off the plane. Can we figure out how far away this point is to the plane? Okay. Well, so one way to do this would be to try and figure out what we know. One point on the plane, 2 minus 1, 4, but it's not necessarily directly underneath. It's not necessarily the point on the plane that's closest to this, right? And so one way to figure it out is to try and figure out what is that exact point right there. But that sounds a little bit tedious. So is there something else we can do? Well, if we make this vector right there, going from the point that we know to the point we're trying to find, right? Well, the distance, the closest line is going to be perpendicular to the plane, right? And that distance there, right, we're forming a right triangle where this vector we're getting is one side, and this is a vector going in the same direction as n. But it's kind of matching the length in the direction of n of that, and that's precisely the projection, right? And so the distance here is going to be, take this vector right here, so minus 3 minus 2 gives me minus 5. 4 minus minus 1 gives me 5. 1 minus 4 gives me minus 3. And so that's this vector right here. is -3 minus 2, 4 plus 1, 1 minus 4, gives me that. And then the distance is going to be the component of this onto n. Okay. So, how do we figure out component? So if you remember, if this is my vector v, component of v onto n, this is taking the dot product of v and n, and then dividing by the magnitude of n. So I need to dot -5, 5 minus 3 with 3 minus 1. So -5, 5, minus 3, dotted with 3, 1, 2. Divide this by magnitude of n, which is going to be 9 plus 1 plus 4. So what do we end up with? 3 times -5 is -15, plus 5, minus 6, all over the square root of 14. So -15 plus 5 plus 6, so this is -21 plus 5, so that's -16 over square root of 14, but distance needs to be positive, so we're going to take the absolute value, and our distance is 16 over square root of 14. And so there's our answer. Okay, and that's all I have for you for this video. See you later.